Boom, we're live. Right?
Yes.
Promise?
Yes.
I guess can people hear you or not?
I don't know. Yeah, they can hear me.
Okay, all right.
We'll
So
all just keep
I never know
quiet
for
then.
sure if it's gonna be like, I'm gonna look like I'm just talking to a ghost or something, talking to myself like a crazy person, or yeah. Anyway, oh, I was gonna talk about James Webb, but I can't because we're gonna talk about James Webb. So I'm not gonna bring up that conversation yet.
Yeah, don't spoil your dinner.
Yeah. Um, so I finally discovered one advantage to living on a mountain, and that is everybody's been complaining about the really crazy fog that's socked into our local city for the last week and a half, and we haven't experienced any of it. It's been beautiful sunny skies every single day, and if I drive down I go into the fog, but for the rest of the time it's just absolutely beautiful and sunny. So it's a little colder, but it's really nice and sunny up here now.
How long is the drive to town, Fraser?
It's about 20 minutes.
Oh, that's not bad at all.
Nope. No, it's, before when I used to live sort of in town, for me to go to the grocery store was a 15-minute drive. And now that I live on a mountain, it's a 20-minute drive. So it's not bad at all. Yeah. But we've got it's the weirdest thing living in the boonies because there's just, man, I don't know how to describe it, but there is just a group of people that just are like a couple of days ago, I stopped some people who had shotguns and were shooting clay pigeons at the end of my driveway.
Oh.
Their truck was blocking my driveway, and I had to walk down and go, "What are you doing?" And they're like, "Oh, we didn't think anybody lived here." Can you not see our house right back there? Oh, okay, we'll go. Yeah, thank you. And that is the second time we've had to sort of kick people off our land for target practice. And this is Canada. So
Yeah.
And then we've had, a couple of times I've been just sort of hanging out gardening and someone just popped out of the forest who was hunting mushrooms. And just random dogs, and yeah, it's a weird thing, but sort of you get the peace and the quiet, except every now and then you just get some person just showing up out of nowhere.
Yeah, that's what the boonies are like.
That's exactly.
We have people coming through our property, either hunting or
Yeah,
just to collect stuff.
Yeah, and as I think back to my childhood, living in the country, that was me.
Yeah, you're the person just appearing out of the woods.
Exactly. Just if your land was in between where I wanted to go, then I was absolutely cutting across to get to the other side. Yeah.
Do you guys have a lot of snow now?
Oh yeah, we've still got about another half meter of snow on the ground. We had about 1.5 meters. Probably 2 meters of snow have fallen total, so it's just been crazy.
So do you ski or something like this, or do you have this kind of cool jet, or how do you call it?
Well, I do ski normally, but I don't have I don't have the facilities. I don't have we're just in a little trailer, so I don't have a place to store all kinds of winter gear and stuff. So we didn't think it would be an issue. And I've got some snowshoes, but apart from that, no, we're just stuck. A couple of times we couldn't even leave our house just because the snow was so bad on the driveway. Anyway, we've reached the 5-minute mark, so let's get cracking on the actual show that we do here. Hello and welcome to the Weekly Space Hangout for Wednesday, January 26th, 2022. Fraser Kane, publisher of Universe Today. This week, we're going to be talking about James Webb, obviously, what it's like to apply to be an astronaut. Very large number of stellar mass black holes in the universe, and a crazy new image of the heart of the Milky Way. Joining me this week, to my right, I've got Alan Versfeld. Alan, how's it going?
It's been great, thanks. Lovely to be here again.
Yeah. What's this is I don't want to spoil the conversation, so I'm not even going to talk about it because it's sort of the local South African telescope, very cool, very local, but we'll get onto that in a second. We've got Dr. Moya here. Moya.
Hi, Fraser. How's it going?
So we've been talking to people who are sort of related to the show, or even people we've been interviewing for the show, and some of them are just in the process of defending their doctorate. And so I've been telling everyone that you live streamed it as like throwing the gauntlet down. Nobody seems to want to step in your footsteps. Any advice? Was it a positive experience, or would you not do it again?
I would do the defense again. I wouldn't do grad school again. The defense, once you get to that point, they're not going to fail you unless there's something very wrong with your advisors. So, and this is the advice that everyone gave me leading up to my defense, and I didn't believe it. I still went into it super stressed, but afterwards I now understand that they were all right. If you have gotten to the defense, you're fine.
Yeah. Right. So you wouldn't have done grad school, but you would have live streamed your defense.
Oh, I guess if I didn't go to grad school first, I shouldn't live stream a defense.
I don't think I want to pull on this thread anymore. All right, we've got Veronica Klimovich. Veronica, welcome back.
Welcome back. Nice to see you all again, or hear you all.
Again, it's like 3 a.m. there or something.
And again, it's 2. I have a late night show with you guys.
Yeah. Awesome. We appreciate your professionalism. You are a go-getter. All right. So before we get into this week's special guest, I just want to remind you that we are also part of an amazing community, the WSH crew. So if you want some space friends, go to wshcrew.space, and they will give you even more space news, a community to talk about things, a way to pick guests to come on this show. And speaking of guests, we've got Dr. Ralph McNutt joining us. Ralph, welcome to the Weekly Space Hangout.
Well, thank you. It's good to meet everybody.
So the question I always ask, who are you? What do you do?
I do space stuff. So I'm
all?
Well, we all try to, I think.
Yeah.
So I'm at the Johns Hopkins University Applied Physics Laboratory. I've been there since 1992, and I've got an experiment flying on Parker Solar Probe. I've got an experiment flying on New Horizons. I'm on the Voyager science team. I'm on the Europa Clipper science team. And I try to make sure that our connections between NASA and DOE keep working. So we've got plutonium to keep running spacecraft out to the outer part of the solar system.
That was a bit of an issue for a while there, wasn't it?
Oh, it was a big issue for a while, and it still needs care and feeding. But things got turned around, and we're in a much better place now than we were.
The plutonium must flow.
The plutonium must flow. That's right.
Yeah. Well, let's now. We've talked about the Parker Solar Probe and New Horizons and all of those quite a bit, but I'd like to talk about the mission that you're pondering for the future, and that is a potential interstellar probe. Let's talk about that.
Well, that's right. So it's a concept that's been around for a long time. Earliest document I've been able to find on it was in March of 1960, right after that NASA had gotten set up. And people have been saying, one of the things we need to do is to find out what the surroundings look like out there. And we sort of started that off after a lot of studies with Pioneer 10 and 11 back in the early 1970s. Make sure you can fly something through the asteroid belt and have it actually come out on the other side. And that worked out okay. And so then we flew the Voyagers, which are, of course, still operating. And we've also got New Horizons up there. But all of these have had planetary targets. And the question is now with the Voyagers that we know where that the edge is of our heliosphere, that's our magnetic bubble that we have within the nearby interstellar medium. You'd like to go a lot further and a lot faster and find out more about what is out there. And right now the Voyagers have only really scratched the surface. So Interstellar Probe is about taking a dedicated spacecraft and going farther and faster than anything has ever gone before.
So how far are you hoping to get in comparison to the distance that the Voyagers have reached?
Well, right now Voyager 1's the farthest thing and the fastest thing. It's moving at about 3.6 astronomical units per year, which is about 17 kilometers a second. And no, I can't do it in miles an hour because I just don't use those units anymore.
Like a billion, I think, or maybe it's 7.
We're a ways out there, and we're going pretty fast. But we're at about 100, and we're a little over 150 astronomical units out with Voyager 1, and the idea, and Voyager 1's also running out of power from the plutonium that keeps the spacecraft running. So, Interstellar Probe is something that we would take a super heavy lift launch vehicle, such as the SLS. We're also talking with people at SpaceX about what you might be able to do with a Starship, and people with Blue about what you might be able to do with the New Glenn. But right now, we've been working with the people at Marshall Space Flight Center for several years on what you could do with an SLS, and putting that with a 50-year lifetime, and looking at something that we could do with current technology and some upper stages. We could get out to between 300 and 400 astronomical units,
Wow.
and on a 50-year mission. So
That's
we'd
incredible.
at least double what Voyager did, and do that by design. The Voyagers were actually designed to last for 4.5 years. We'll be at 45 years this summer, so it's outlived its warranty by a factor of 10.
Yeah.
Which would get you into trouble with some other commodity markets in the world.
But it is very interesting that Voyager has really taught you what the limits of power are on a deep space probe like this using an RTG. 45 years, almost out of power. So I think 50 years sounds like a pretty great mission lifespan.
Well, 50 years we think would be, and we think we could probably get a little more time out of it. It's an interesting problem, though. In the course of this study, one of the things we had to address was, well, suppose we tell everybody we've designed this thing for 50 years. How do you convince them of that? And it turns out that's a pretty hardcore engineering challenge, because people do not design spacecraft to last for 50 years. People don't design much of anything to last for 50 years without some kind of human intervention. Yeah. So it's actually been an interesting part of the problem about what you can do and how far that you can go with a spacecraft like this.
It's interesting. People always ask me, why don't they build a Voyager 3? And it sounds like this is Voyager 3. So let's talk about the instruments on board. How would it be different from the Voyagers? Because I'm even looking at the picture, and it kind of looks like a Voyager.
Well, there's a reason for that. It's a lot of the things that we're still trying to understand that the Voyager scratched the surface on. We've gotten a lot better with the technology. We've got a lot better with the measurements. And I've told people, well, there's a reason that it looks like Voyager on steroids. The high gain antenna is 5 meters in diameter, and the reason for that is you've got to be able to communicate back from these really, really long distances. Right now, the Voyagers have got 3.6 meter diameter high gain antennas, and we get a data rate of 160 bits per second coming back from the spacecraft. We are tracking them. Right. And that's coming in from a light day out. So as you get further and further away, the data rates go down. So one of the things we would do is design this to have more power going to the transmitters, first coming down to the Deep Space Network, but also looking at extensions to that, maybe with the next generation very large array. We've been talking to a lot of people around the world, actually, about, because other people from other countries have said, well, what can we do to contribute to this project? And I've said, build more high gain antennas for downlink. Right. And, you can participate in the science, and it'll be good for everybody.
You could use the square kilometer array.
That's another one that we have been talking to people about. It's a little trickier. It's not quite plug and play, but nonetheless, the plans are out there, and these are the sorts of assets that one could think about. And one of the reasons that NASA asked us to do this study was to take a look at exactly some of these, real world problems and what would be some of the issues that we'd have to think about if, we decided this was a good thing to go ahead and do. So the study was done actually to look at a wide variety of instruments that you might want to fly. It's kind of it's a little bit of a Christmas tree, but what we've done is we've basically set this up as a menu and said, well, you don't have to order everything from the menu, but so you can think about a subset, and this at least gives you an idea of what you might be able to do, and might be able to give us the appropriate tools for really filling in the knowledge gaps that the Voyagers have left. And the good news is we now know where some of those gaps are. The bad news is, of course, we don't have anything out with the Voyagers right now to make some of the necessary measurements. But we would know how to do it on the next one.
So, I mean, I'm thinking about, like, with the Voyagers, a lot of the effort was put into their planetary work, imaging Saturn, Jupiter, their moons. Voyager 2 got a chance to do the flyby of Uranus and Neptune.
Right.
Would you be able to take advantage of some flybys as well?
Sure.
Maybe
If you
hit one of the ice giants, please.
Well, on all the trajectories that we've looked at, we'd be going by Jupiter. If you want to go by Uranus and Neptune, you'd end up having to go down the so-called heliotail, sort of in the opposite direction from the incoming interstellar wind. But basically what we've looked at are all sorts of different mission scenarios. And right now there's a thing going on in the U.S. called the Solar and Space Physics Decadal Survey. That's just starting up. And that'll be about a 2-year-long effort for people from the science community to give recommendations to NASA and the National Academies of Science about what we should be doing over the next decade. And the study that we did is really input to that deliberative body. And we'll see what happens in 24 months. Hopefully we've made the case of being able to convince everybody that, it's now the time to think about really doing this. And if they said, yay, verily, you guys are right, we really should be doing this, and everything lines up right, well, then might have a chance to actually fly the mission.
It's interesting. I just interviewed the people from Project Lyra. I don't know if you're familiar with that mission to chase down Oumuamua. And it's in the same kind of regime. It's like a 26-year flight, a bunch of flybys, a big launcher. So maybe there's a way to kind of like combine some of those ideas. But what is going to be out in that distance, that incredible distance, that you wouldn't experience being closer in with the Voyagers? Like, you're expecting something dramatically different out there in the interstellar void?
Well, it's a trick question, and the answer is, well, we don't know. That's the reason we're going. One of the things that was interesting was that everybody had said that, well, by the time you get to the so-called heliopause, which is sort of the dividing line between the plasma and the particles, the energetic particles coming from the sun, and what's out in the interstellar medium, that you get past that and the interstellar medium was going to be dull and boring. Nothing was going to be going on. Time scales were going to be measured in centuries. And of course, the Voyagers have already told us that, nope, doesn't look a thing like that at all. There's all sorts of actual input that's coming in from the sun that's still getting out into the nearby interstellar medium and affecting what's going on with the dynamics out there. That was not something that, was sort of a question of, well, who ordered that? I mean, we basically do not understand the physics still. And so a big question is, well, okay, so how far does the sun's influence really extend? And what can we learn about the interstellar medium? What can we learn about the dust that's out there? We may be able to see innermost vestiges of particles from the Oort cloud, perhaps, or perhaps not. We're still getting an idea of what's going on with the nearby local bubble that basically sets up the pressure that contains how big that our bubble is. And that has a lot to do with shielding us down here on good old Earth from galactic cosmic rays, for example. So there's a whole bunch of things that we're still trying to sort out. There's models of the interaction. There's all sorts of computational models. There's a good dozen of them, and so far none of them have been able to duplicate the Voyager measurements. So
That's weird.
there's still things to learn,
Yeah.
and that's why you go to places you've never been before, and we've never been that far out there before, and the Voyagers are going to go offline before that we get as far as we could with something like this.
So what do you envision as like the greatest challenge to sending a mission out that far?
Getting to the launch pad. Seriously,
Yeah.
I worked on New Horizons with Alan Stern from the very beginning, and Alan is always fond of saying that it took longer to get New Horizons from Washington to the Cape than it did to get it from the Cape to Pluto, which is right. These things
are
a
long time to get to Pluto.
Well, exactly. Well, I mean, it's in Parker Solar Probe, which is up there now and doing absolutely breakthrough science, getting down into the corona of the sun. Actually, APL started working on that for NASA in 2001. It took us 17 years to get it to the point where we could launch it. About 10 years of development, and about another 7 years of people making up their minds, getting all of the stakeholders to say, this is something that really should be done. And so it takes a while. I mean, there's a lot of money at stake in all of this. There's a lot of people that get involved, and all stakeholders want to be sure that whatever you're doing, that first of all you do it right, and second of all, or maybe first of all, that everybody's getting their money's worth out of it, because you really have to think those things through. But nonetheless, this is the way that science advances, and right now the Voyagers are going to be coming into their sunset. New Horizons is probably good at least until the early 2040s. But if we don't start doing something right now and get the plans moving, there won't be another American space probe out there. Maybe one from China. The Chinese are taking a look at perhaps launching something. So we'll see what happens. But it's something that's important, I think, for everybody for somebody at least to go out there and find out what's going on and get a better idea of what our home really looks like from the outside.
So now that James Webb has launched and the sort of enormous budget gobbling sort of monster is now out in space, I'm sure everyone wants to sort of think about giant technical risk again. Are there any ideas sort of out there that you kind of really like that you would love to maybe test out? I'm thinking about things like the electric sail or a mag sail, like some pretty great ideas on how you could potentially accelerate a spacecraft. Maybe the work that Breakthrough Starshot is. Any of that, apart from a big old rocket, are there any ideas that you would love to try and explore a little further?
Well, there's things out there that are important for us to do, and I mean, of course, we've got this one on a big old rocket, because the big old rockets are something that have a near-term technological realization. I mean, at some point, we're going to really need, if we're going to really expand what we're doing with people, if we're going to expand what we're doing with automated spacecraft, we are going to have to get some sort of fission reactors working up in space, and it's a lot harder to do than people have usually thought, because we've tried it multiple times. The United States has flown one reactor in space. That was in 1965. Worked for 43 days.
Yeah.
The former Soviet Union former Soviet Union's setup has flown about 30 of them, and they lasted for somewhere between about 6 and 18 months each.
Yeah.
So there's lifetime issues, and if you think about it, again, most things that you build, you've got some human being that can always take a screwdriver and a soldering iron and go fix them, but it doesn't work that way for space probes.
Yeah. And I guess, I mean, that's the thing, is I think the the lesson that James Webb unfortunately taught the community was just be careful with the amount of risk that you try to take on simultaneously in one mission. It gets complicated and expensive very quickly.
Well, and things that get complicated get expensive, especially when you're doing them in space. But you know, the fact that James Webb is up there and running, I mean, this is going to be an incredible boost to our knowledge of the universe by having that working. But on the other hand, of course, you know, when it was first proposed, if you'd told people at the time that, oh, by the way, it's going to cost $10 billion, it probably wouldn't be up there now.
Yeah, it is funny. Like leading up to James Webb, everybody was so nervous and quite sarcastic about the mission. But now that it's launched, everyone is so excited. Like I just can't believe just this pure enthusiasm for this telescope, which is wonderful. So if all goes well, the Decadal survey gives you the thumbs up. What would be a launch date that you would like to see, that you think is feasible for this mission to take off?
Well, you know, what we told everybody was that we need to have something that the technology be ready by the 1st of January 2030, to have a line drawn in the sand about that. What we've done is that with all of these trajectories, you have a Jupiter flyby. Jupiter goes around the sun once every 12 years. And so depending upon where you are in that 12-year cycle, that's going to tell you where that you could go. We could go by a variety of Kuiper Belt objects on the way out, such as Quasar and its moon Weywatt. Uranus and Neptune, we have to sort of go the opposite direction from the interstellar wind. But one of the things that we've looked at in the study scenario would be a launch around end of the summer of 2036. And be able to go out sort of to the side with an energetic neutral atom camera to be able to actually take a picture of the heliosphere from the outside and see what our home in space really looks like for the first time.
So the direction really matters.
The direction does matter.
Yeah.
And typically what would happened on Parker. Typically what NASA does is if there's a decision to go forward after the decadal comes back and if everything comes up green, NASA put together a science, space technology and science definition team, and to go back and look at what we've done on this study and look at anything else that's come up, look at what else has been in the decadal, and start to make some decisions about, well, you know, which direction would you like to go and which direction makes sense.
Yeah.
And so there's a lot of things between now and actually getting this to launch. But you know, where there's a will, there's a way, and you have to start somewhere.
Yeah.
So
2030.
So mid 2030. Stay tuned. We'll see what happens.
Just around the corner, and maybe it's a shorter trip from Washington to Cape Canaveral in this case.
Hope so.
Before we let you go, I just want to make one, I guess, plea with you. I don't think the name is right, because I've had a lot of people say, "Oh, they're going to try and send a spacecraft to another star with the Interstellar probe," and I'm sure you've seen that too. So I'm, you know, Voyager 3. I'm telling you, it'll sell big. It's a remake. It's a reboot. Now's the time. Voyager 3. That's just my.
So you should, you know, if that's what you think we should do, well, then you should go out there and start up the lobbying effort.
I will.
I'm afraid the name's above my pay grade on this one.
I'll make a video all about it then. Talk about the mission and specifically suggest Voyager. Tell people that it's a sequel to the Voyagers, and I think people will be totally on board. Ralph, if people want to track what you guys are working on, not just this, but all the missions that you're involved with, where should they go?
So we've got anywhere on the Johns Hopkins University Applied Physics Laboratory website, which you can Google and easily find. But for Interstellar Probe in particular, we do have a website. It's got all the information. There's also a sign up.
My guess is Pamela stepped away from the computer, left her phone, and it was dinging. Okay. Yeah. Yeah, we're live right now?
Oh.
Okay. All right. No, but Wirecast went down. Yeah, okay. Bye, Nancy. Okay. All right. Perfect. People can hear me again. I think this technical issue was a perfect segue to our next part of the show. Moya.
Perfect
Black
segue.
holes. Yeah,
Black
perfect
holes.
segue.
Okay. Yes. So this headline is that there are 40 quintillion stellar mass black holes in the universe. I don't
But
love
wait.
this headline.
People,
tell
hold
you
on.
why.
People are saying they only hear music, so I was absolutely sure that everything is back and it's fine. Yeah, it looks fine to me on YouTube as well. All right, proceed, Moya.
Okay, we're going to talk about these black holes. This is a new estimate from a study that comes out of the International School of Advanced Studies, or CISA, in Italy. And it says that there are 4 times 10 to the 19, or 40 quintillion, black holes in the universe that have masses less than 10 solar masses. These are what are called stellar mass black holes. These black holes usually form from massive stars exploding at the end of their lives after they stop fusing. They are the smallest of the black holes. We're not talking about supermassive black holes here. This study, simply put, simulated stellar formation and evolution in galaxies around the universe and basically just counted how many black holes there should be using this very sophisticated simulation that took into account.
So they simulated stars living and dying, counted up the number of black holes that were formed in their simulation, and then extrapolated that to the entire observable universe.
Yes, basically.
Got it.
In their simulation, they took into account the star formation rate, which means they had to make an assumption about the initial mass function. This is when you get a cloud of gas that forms a bunch of stars, the initial mass function tells you the distribution of those masses. So they did have to assume that. In case anyone is interested, they used a Krupa IMF. So they took into account star formation rate and the IMF, they also took into account chemical evolution over time for these galaxies and the merger rate for black holes. So this is on a bigger scale than this type of study has ever been done before, which I was kind of shocked to see. But this does take a lot of computing power to do this type of universe-wide simulation. They also varied the codes that they used to simulate these stellar evolutions. And so they used a couple different codes. 7 and cosmic were the ones that they used. And they found that it really only affected the models at the high end of the mass range. But what they found, these 40 quintillion stellar mass black holes should account for about 1% of all of the baryonic matter in the universe. And the baryonic matter itself only takes up about 5% of the matter energy content of the universe. So we're talking about a very small percentage here, but still a lot, I guess. But this number isn't new. This is why I didn't love the headline of the article. The old estimate that I remember hearing, the estimate that I cited in my book, was that there are about 10 million stellar mass black holes in the Milky Way galaxy. That estimate goes up, or it used to go up, to maybe about a billion.
100.
Yeah. And so I got really excited when I saw this, excited and nervous, because I thought maybe I would have to go back and change the book. But then I did the math.
40 quintillion divided by
divided by like 100 billion, and so it ends up working out, which means this isn't the big revelation from this paper. And in fact, the title of the paper, and not the title of the article that was about the paper, was The Black Hole Mass Function Across Cosmic Time, because that's what's really interesting about this study. It was novel to see the black hole mass function evolve over cosmic time at different redshifts. So if you go to the next image, you'll see this plot from the paper that shows the mass of black holes on the x-axis, and then they had some complicated y-axis, but it's basically like how common are black holes, and then they have it for different redshifts, so different snapshots of cosmic time. And what you see is that the black holes are more prevalent in modern times, which maybe you might have expected, but I don't study black holes, so I didn't really expect that.
Well, no, I mean, okay, so hold on. So if you would ask me, like, I would have expected that we would have had more black holes when the most star formation was happening in the universe, and that was just 3-4 billion years after the Big Bang.
Right.
And so you would expect all of the black holes.
They would be accumulating, sure, but
from what I understand, like the amount of star formation was ridiculous back early on, and the stars that form black holes only last a couple of million years. So from cloud to black hole isn't a long wait. So what you're saying is, in fact, they're accumulating more slowly than you would anticipate?
I'm not sure. They did take into account the merger rate, if that's what you mean about accumulating. But there are a lot of factors at play here. It's yes, star formation used to be a lot higher, but the metallicity is changing, and the metallicity will determine how likely these stars are to turn into black holes, and that affects the rate of stellar evolution. And then as the black holes combine, that would technically decrease the number of black holes, even though they would have had time to accumulate. So there's a lot going into this distribution over time. But when they get the chance to study this more, because this is just the first paper in a series about the black hole mass function, they hope that it will help give them perspective to answer the mystery of how we got so many massive black holes early on in the universe, less than 1 billion years after the Big Bang. So we don't know why they're there. We see these really high redshift galaxies with massive active galactic nuclei. We don't know how they form so quickly, and so hopefully this study will get us there.
But it sounds like it doesn't.
I agree, but it's just the first paper in the series, so we'll see where it goes.
Right. But it sounds like you didn't get this enormous preponderance of black holes early on merging and creating these supermassive black holes, because some of the most earliest observations, some of those distant observations by Hubble, etc., are already seeing supermassive black holes just 1 billion years after the Big Bang. Less
than. I saw one that was like 600 million years after.
Yeah. And so and then if you're saying, well, actually the black holes took longer to form to really build up, though those don't align.
Right.
So that's really interesting.
Yeah. So I think that the point of this was more looking at the number over time, not the formation rate. and at the mass of different numbers. And they did in the paper make a big deal about how you can see in this curve that it's relatively flat until about 50 solar masses for the black hole, where it starts to drop off. And I think that was one of the interesting findings. They didn't answer this question yet, but I have hope for the future papers in the series.
Very cool. Still, it's nice to, I mean, we went with that number too in Universe Today, right? 40 quintillion. It's such a wonderful number. And I love the idea. Like, I was torn. Like, do we just go with that there's only 1%? Because I'm always like, people are always telling me, oh, the supermassive black hole at the middle of the Milky Way is like the anchor for the whole Milky Way. But actually, it's not. It's a fraction of the mass of the Milky Way. It's nothing.
Yeah, if you take all the stellar mass of the rest of the bulge of the Milky Way, it's 1,000 times heavier than the mass of Sagittarius star.
Yeah, you could ditch that black hole and nobody would notice. Yeah, awesome. All right, Veronica, let's talk about being an astronaut. So
okay.
So what happened?
What happened? So there's as maybe some of you know, there is like an astronaut selection process going on in Europe. It's a big deal because it's happening only once in 10 years, and all European countries can apply. Like, I don't know the number, but maybe 16 countries and the partnering countries as well. So there's a lot of countries and kind of a lot of competition, and it's happening very rarely. So everyone was excited. So they announced the selection process in March, and I applied.
Yeah.
In March and April, yeah. The process would normally take 6 stages, like the general CV, cover letter, answering questions. The first stage. The second stage are psychometric, psychological, orientation, some kind of tests, like very personal ones. And this is stage 2, and it takes like the whole day. So you're sitting and doing the test. And I was invited to this one. And the third one is like also psychological test, but the most probably group exercises. That's what was done like in the last selection 10 years ago. And unfortunately, I was rejected for that one, so I'm out of the run. But I'm excited for the friends.
So I had heard that there was something like 26,000 applicants they were considering, and then they knocked it down to like 1,300. Made it to the second stage.
Right. You could see it on the screen. I just added very quickly the statistics from ESA. So there were like 23,000 valid applications, because there were a lot of other which are not valid. Yeah. And you could see like that for the stage that I was taking, which is the second one where you have this personal interview, there was like 1,360 people invited. And what is interesting is the percentage of women and men, of course, and they were putting a lot of pressure. Not pressure, I mean opposite, like they were like empowering women to apply. So and also the second circle that you see on the screen maybe is very interesting as well. They were selecting para-astronauts, so the people with the disabilities, and basically they would choose few of them to see, like to basically like train them and to see how the disabilities and what kind of disabilities influence being an astronaut, and basically to come to the conclusion whether disabled people can be astronauts as well. I think it's really cool.
That's really cool. I mean, you'd think in weightlessness, certain disabilities are no longer an issue.
Yeah, so they've chosen, I think it's like when I was reading the medical section, they said like for the para-astronauts, mainly people without limbs, which makes also sense. Like because in weightlessness you don't really need legs to will be frank.
Yeah.
All right. So there's some disabilities, or maybe even like there's a lot of things to do in space for future, and to know how the different disabilities affect working in space is a good thing to start early on, because even more people can fly to space.
And so you went through the interview process. Was it intense?
Yeah, it was super intense. It was basically, it took ages for them to reply because of the 23,000 applicants. And then we were like invited continuously over like a period of 6 months in different groups, and you had like 1 month to prepare. And basically that the preparation is the tests are similar to those for the pilots. So if you find like some like software preparation for the tests for pilots, they are like very similar. So they were testing your memory, they were testing like your orientation ability, your language skills, a lot of psychological questions, and it's very intense. So the tasks, like when you do the task, like 15 minutes doing of this task would just like tire you, and you need to do it like for like, I don't know, 5 hours or
wow,
how many hours, 6 hours or something. So they're very exhausting, and you kind of have to be fit, very fit. So I was using like all the tricks, like, I don't know, meditation, breathing, whatever, like just to stay focused. And it helps, like those people who I know who like went to the next stage, they were also using like all possible tools to stay focused and concentrated. And yeah, it's a fun. And I have friends who got in, as I said, in the next stage.
That's amazing.
And now they're like going crazy with it, like, how do I prepare? Should I say? Like, what I need to do in the group selection? And yeah, exciting time. So I can, once I know like some insider information on how it's going on the next stages, I can report about it again.
That was my hope. My hope is that you would get selected, and then we would be able to do an episode and interview you while you were, say, training or on your way, and find out what it was like. But we'll, still, I think it'll be great to find out the inside track as some of your friends get further into it. Let's talk about James Webb.
Yeah,
what happened with James Webb? Oh, she muted.
Apologies.
No problem.
Of course, the technique is not working when it's supposed to work. Okay, so James Webb finally reached its orbital destination, which is around 1.5 million kilometers or 1 million miles away from Earth. It took only like 5 minutes of thrust firing to put James Webb on this halo orbit with at the Sun-Earth Lagrange 2 points. And the commission manager, he iterated that the efficient the launch of the Ariane 5 and the maneuvers have been, and this efficiency allowed for the James Webb to even get a more lifetime as originally announced. So now they are approximating 20 years of the lifetime for the James Webb mission instead of 10 originally. It's not 50, but like 20, I think it's pretty impressive as well. So, and yeah, basically they would need to do some correcting maneuvers every 21 days, but they have enough fuel, as I said, for approximately 20 years of work.
So what happens next with James Webb? For the people who are watching the ongoing mission, what's the next step?
So basically the next step is calibrate the mirrors. There are 18 mirrors that should work as one large 6.5 meters telescope, right? So the calibration of the mirrors will be done to 1/5,000th the width of the human hair. So it's very, very precise. And there is a special technique that they would use to calibrate and align the mirrors. So they will be watching a bright and isolated star on the sky. And the first the 18 pictures or images would be delivered, which will be very blurred at the beginning. But then they will start this very slow and long process that they call phasing, which basically do the alignment of these mirrors to get the nice pictures for us. And if some people are curious, the stars that they have chosen for this process is called HD 84406. very impressive name, but it's something similar to our sun sun star, and that's basically what they will be doing next few months.
Yeah.
I actually read different timelines. It's either months or 3 months for this kind of process.
Yeah, I've heard 5 months, but
you
still,
see.
I mean, I think it's going to take as long as it takes. I mean, they don't know how long it's going to take to align each one of these mirrors, and it could go faster, and it could go slower. It's funny. It's so similar to like when you do astrophotography, the first pictures you take, you find some star that's what you need, and then you just take a whole bunch of pictures and try to nail the focus on that one star before you then move on to actually taking other pictures, because if you don't have that, you don't have the focus working, then nothing else is going to work. But that's obvious. Awesome. All right, we're running out of time. Alan, you had to switch internets. You're okay now?
Yeah, one broke. I got another one. So here I am.
Perfect.
Yeah.
So let's talk about this incredible image of the Milky Way.
Yeah. So this is actually expanding on data that was originally captured back in 2018 when the Meerkat array was being first commissioned. Back then, they put out something that was a small portion of this image. This is massively refined and a great deal bigger. This image covers what is it? 60, I think, square degrees. 6 square degrees. Sorry. So it's about 34 students that they're covering here. Yeah, no, it's really interesting. As this was 3 years worth of analysis done in a pair of supercomputers hosted in Cape Town, which are all going to be parts of the back-end infrastructure of the SKA when that's finally commissioned. What we're looking at here is this is all done in the radio, obviously at 1.28 gigahertz. If that means something to you, it's a slightly higher frequency than the famous 21 centimeter hydrogen line. I'd sort of hoped it would be the same because then I could explain that, but it's not. So sorry. Yeah. So this is a really cool image. I mean, it's not just. I mean, it's very striking. You know, the colors that they've chosen, where basically anything in black and white is a very low, is a very low brightness signal, and anything in color is the very bright signal. So it looks like they've taken 2 different calibrations and overlaid them to try and show the detail at all the different brightnesses.
I just see a bunch of faces in this picture.
Let me have a look, see if I can find them as well.
That's because your brain is built to see faces.
I know.
I mean, there's one on Mars. That one we know is real, but these are,
Oh yeah. So I know one of the really interesting puzzles that they had originally identified back in 2018 has gotten even more interesting are these filaments that they're detecting.
Yeah, I mean, these are just filaments of presumably gas or dust. Still don't know what they are. And the hope is that with this much more detailed image, we can maybe start to piece together exactly what's going on there.
Yeah, they found like 1,000 of them in this picture.
Yeah. Actually, this picture has got one on the sort of top right half, but you'll see that streak on the bottom left. They've identified that. That's a neutron star that's been ejected and is hurtling space at whatever speed. It's just stunning. And all these bubbles, like right at the center, there's supernova remnants in there. There's a whole list of just cool stuff to see. It's in fact, this picture, they call it the one that was just on, they call it the mouse and the snake. The mouse being that neutron star and the snake being the filaments. I guess they thought it looks like the one is chasing the other. Pretty cute, I thought. Yeah, I mean, they've got outbursting stars in this image. There's star forming regions, and the sort of grand scope image, you can just make out the edges of one edge of this massive radio bubble that was identified a number of years ago. And
Meerkat is
stunning image.
Meerkat is like the precursor, the Pathfinder technology for the square kilometer array. And so this is just an appetizer for what we'll eventually see with the square kilometer array. Yeah,
I mean, Meerkat is 64 dishes covering a range and a diameter of about 8 kilometers. the finished project is going to be thousands of dishes over thousands of kilometers. I mean, can you imagine? Every time I talk about this, I end up saying the same things, but I still haven't quite wrapped my mind around it.
Yeah, and it's such a tricky part of the Milky Way to observe because it's so filled with dust.
Well, because that's the benefits of radio. You can cut right through that, and we're doing that. And of course, it helps being in the southern hemisphere. At our latitude, the Milky Way is directly overhead. So we've got this beautiful, clear, all-sky view. Even naked eye, it's glorious.
You're so lucky. You're so spoiled down there in the south.
Oh yeah.
Have you ever experienced it? Have you ever stared up in the sky and seen the Milky Way as opposed to seeing it just down by the horizon?
Yes, I have. I went to Chile once and it was so dark. I saw my shadow cast by the Milky Way.
Oh, that's incredible. Yeah. We were in Australia and it's this really weird thing of you're looking straight up and seeing the all of the nebulae at the core of the galaxy, and then seeing like Saturn and directly overhead. That's just not right. That's just it's not fair is what it is.
Well, you guys get the Polestar, you get M31.
Sure.
You've got most of the Messier catalog.
Yeah, no, it's true. Well, only because Messier lived in the northern hemisphere. Come on with it. It's an amazing picture. It's an amazing science story, and I think that this, I think this is a teaser for what comes as we approach the completion of the Square Kilometer Array 2030. Just more of this. Yeah.
Looks like something.
Yeah. Was there anything else that sort of jumped out at you with this story that you wanted to cover, or should we move on?
Really, the only thing extra is just that the full data is on their website. It's we can paste a link somewhere, but I mean this is more for professional use. These are gigabytes FITS files, so amateur like me can't do much with it. But to professional, this is gold.
Yeah. FITS aren't that hard to work with. You just have to, you just have a fast internet connection, and then you can decode them. Hubble has a pretty cool FITS viewer that you can actually use. Awesome. Very cool. All right. So Alan, you just talked. So why don't you let us know what you're working on and where people can find out more?
So all my effort these days is on the urbanastronomer.com website and podcast. The website is coming back to life with actual written content, which is how we all got started. So you can find that at urban-astronomer.com, and updates I'm tweeting on @uastronomer.
Fantastic. Moya.
Hi, you can find me on Twitter at GoAstroMo. I host a podcast called Exolore that's all about fictional world building using science, and I wrote a book. It's coming out in August, and you can pre-order it now if you go to the pinned tweet in my account. It's really exciting.
And a video series with PBS.
Yes, all about mythology. So if you want to leave some space content and go learn about mythology from around the world, I'm hosting a new show with PBS on YouTube called Fate and Fabled.
And is there like an astronomical connection to it as well? I mean, it's got to play into it.
I mean, definitely. I see the overlap all the time. We did an episode, it will come out. We just recorded an episode about constellation myths. So you have that to look forward to. And
Perfect.
We're going to do a collab with Spacetime with Matt O'Dowd.
Oh, great.
Yeah.
That's awesome. All right, Veronica.
You could go to Gaia Aerospace webpage, and there you could find our community of new space companies in Germany and German-speaking area. So see a lot of fun stuff there.
And if people want to follow you specifically, that's the best way to do it?
I am not following. I'm like antisocial currently. Other than
you just went through the gauntlet, so it's understandable. You need a minute.
I'm like currently I was not supporting any social media. Apologies. I'm on LinkedIn if you want to send me a message.
Perfect. Yeah, there you go. Wonderful. Okay, and obviously I'm Universe Today on all the things, so definitely check out the interesting we've been reporting. We've been covering a lot of the stuff we talked about here, as well as a lot of other great articles. So, all right. Well, thank you, everyone, for joining us this week on the Weekly Space Hangout. Thanks to all of my co-hosts arrayed before you right now. Thanks for a special guest. Thanks to the moderators, Pamela, for engineering behind the scenes. And thanks for everyone watching us both on YouTube and on Twitch. And we will see all of you next week with a big guest. So make sure you come back for next week. We're going to have Dr. Cyan Proctor, who went to space, and is going to tell us all about it.
Nice.
It is next week, right, Nancy? Or is it like 2 weeks? I think it's next week. I'm sure it's next week. If it's the next guest, anyway, she's the next guest, and it's going to be amazing. I can't wait to talk to her. All right, thanks everyone, and we'll see you all next week.
Bye.
Thank you. Bye.